5A. Kinematics of two-dimensional motion. 5.1. Position vectors in two dimensions. Analyzing position and motion in two dimensions is only slightly more complicated than analyzing one-dimensional motion. Positions, displacements, velocities, and accelerations in two dimensions are all vector quantities that can be resolved into their components. You then can analyze the components using the equations of motion derived in Chapter 3. In straight-line motion, you located an object by its position on a one-dimensional number line using coordinates. In two-dimensional motion, position is determined using the rectangular Cartesian coordinate system. Conventionally, the x-axis is horizontal and the y-axis is vertical, but any orientation and labeling is permissible as long as positions, directions, and angles are measured consistently within a given problem. Position in two dimensions is determined by the position vector, r. The tail of the position vector is at the origin of the coordinate system, and the head is at the object's location. Figure 5-2a on page 94 shows the path of a fly on a window pane. At time t1, the fly is at the tip of r1. At time t2, the fly is at the tip of r2. At time t3, the fly is at the tip of r3. The origin is at the lower left corner of the window. Figure 5.2b shows the same part of the fly, but now the origin is at the center of TE window. Although the positions of the fly are identical, the position vectors are different when measured from the different reference points. A frame of reference is simply the coordinate system within which motion is measured or observed. There are an infinite number of reference frames, and, as far as we can tell, there is no fixed center of the universe, frame of reference theorem, which all motion may be measured. 5.2. Displacement in two dimensions. The displacement d of an object is its change in position, represented by difference vector delta r. The displacement for an interval of time is d equal delta r equal r2, r1, where r2 is the position vector at the end of an interval and r1 is the initial position vector. For instance, the fly's displacement, d1, for the interval t1 to t2 in figure 5.2 is d1 equal r2 minus r1. For figure 5.2a, or d1 equal bold r2 bold r1. For figure 5.2b, the displacement is the same no matter which reference frame is used. 5.3. Velocity and speed in two dimensions. Average vector velocity and average speed between two positions in the Cartesian plane are determined just as they are in one dimension. Use vector notation when describing average vector velocity in two dimensions. Average velocity, v bar equal delta r over delta, t equal d over delta t. Average speed, v bar equal s over delta t. The instantaneous velocity vector, which is the velocity of an object at any given moment, always points in the direction that the object is moving at that instant in time. Figure 5.4 shows the instantaneous velocity of a car traveling around a curve. At time t1, the vector points east, but at time t2, the vector points north. In two- or three-dimensional motion, direction is indicated by the vector angles. The instantaneous speed is equal to the magnitude of the instantaneous velocity. Velocity, cheer, absolute v. For instance, in figure 5-4, if absolute v1 equals absolute v2, and absolute v remains constant through the curve, the speed of the car is constant. Depending on the path an object travels, the average speed v bar and the magnitude of the average velocity bold v bar may be quite different. These quantities are equal only if s equal absolute d. 5.4. Acceleration in two dimensions. A vector can change in any of three ways: magnitude only, direction only, or both magnitude and direction. Most real motion involves the third kind of change. Recall from Chapter 3 that acceleration is the rate of change of the velocity vector, delta v. The average acceleration vector, ae bar, is equal to the velocity difference divided by the time interval of the velocity change. A bar, Schachter, v2, v1, over delta t, equal delta v over delta t, 5.1. The direction of the average acceleration is always the same direction as the velocity difference vector, regardless of the direction of motion. For example, as a car slows to a stop at a traffic light, the magnitude of its final velocity is less than the magnitude of its initial velocity. So delta v points in the opposite direction from the car's motion. Therefore, as the car slows, a bar points in the opposite direction from v. When a moving object changes direction, its acceleration vector is always at an angle to its path. As with velocity, acceleration direction is indicated by a vector angle. The instantaneous acceleration of an object is its acceleration at a particular moment. Its vector also points in the direction of the instantaneous velocity difference vector. In two-dimensional motion, determining the instantaneous change in velocity can be fairly complicated without the use of calculus. We will limit the discussion of acceleration to problems where either direction or speed vary, but not both. As with one-dimensional acceleration, if the acceleration is uniform, then the average and instantaneous accelerations are the same.